right? So let us having understood about the phase diagrams, and having understood different heat treatment processes, now we are better situated, better positioned to understand various important engineering materials. So let us start right away with metallic materials. So if you take the metallic materials, typically you can classify them into two broad categories. One is ferrous metals, the other one is non-ferrous metals. We all know ferrous means it is iron related. In other words, iron being the principal constituent in the material. If you ask me whether you have iron in the non-ferrous materials, definitely you will be having iron in some of the non-ferrous materials, but not as the principal constituent or the major element. Okay. So very minor amount, like say from 0.01% to some trace amount to say some 1%, 2%, but not as the main constituent. Okay. So let us start with the ferrous metals, which are the most important engineering materials, especially the metallic materials. When I was discussing about the iron carbon equilibrium phase diagram, I already told you that iron, is the ferrous material system is the most important and widely used popular material system because of the advantage of having a class of a range of materials that you can get from this system. Okay. So let us see what are those different materials that you can get from this steels, ferrous. You have, for example, we already know steels and cast irons, and again you know what is a steel, we already discussed. So within the steels you have low alloy steels and high alloy steels. We will discuss what is a low alloy steel and high alloy steel. And typically this low alloy steel we also call high strength low alloy steels, which are also called micro alloyed steels. So micro alloyed means your alloying elements are of very minimal. The quantity of the alloys that you are adding is of very less in quantity. Let us discuss it in detail eventually. So within this low alloy steels, you have low carbon, medium carbon, and high carbon steels. And you have again in low carbon steels, you have plain carbon steels. You have high strength low alloy steels. These are the ones you actually call them micro alloyed steels. High strength low alloy steel or micro alloyed steels. Similarly, you have in medium carbon you have plain carbon or heat treatable steels. Or again in high carbon you have plain carbon or tool steels. Whenever you say a plain steel, or plain material, what do you mean by that is you are not adding much of an alloys, alloying elements. It is just iron and carbon. So then if you add, say for example, nickel or chromium, or manganese, magnesium, such alloying elements, then you don't call them plain steels. Then you call, depending on what kind of alloying you are doing, you may call it high strength low alloy steel or micro alloyed steels, both are the same, or heat treatable steels, where you may be having alloying elements to make it more heat treatable, or you have stainless steels, you have tool steels. These are different from simple plain carbon steels where you don't have much of alloying elements. Similarly, when you come to the cast iron, you have different variety of cast irons. Now grey cast iron, ductile or nodular cast iron, white cast iron, malleable cast iron, compacted graphite cast iron. Let us see what and all these and how these are different from one another. So coming to the steels, we just saw that low, medium and high carbon steels we have. So if you say low carbon steel, what do you mean by it? Your carbon percentage in the alloy is less than 0.3%. And typical uses for the same, this material is like your common industrial products like bolts, nuts, and all these things. Similarly, for medium carbon steel, what do we mean by medium carbon steel? If you have carbon somewhere from 0.3 to 0.6%. You please remember that this 0.3% and 0.6% is not exact. There is no logical boundary for these steels to call them like that. It is only for our understanding. It is just about 0.3 we take it. Some people say it is 0.25%. So never confuse with the exact number, but you should have some feel so that we are giving some numbers. Okay, if it is say less than 0.25 or 0.3, it is low carbon, and if it is between 0.3, around 0.3 to around 0.6, it is medium carbon, and similarly if it is beyond 0.6, it will be high carbon steels. Okay, and of course in high carbon steels, carbon percentage will not be beyond 2 definitely, because they will become cast irons, and for practical purposes we may not use high carbon steels having carbon more than 1.4, okay, around that range, okay, because it becomes highly brittle in nature. Okay, and of course high carbon steels typically we use for tools, because they are having, since we have a very high carbon, higher the carbon, we know that hardness will be correspondingly high, because they have good hardenability, right? So accordingly we use them for tools where you need high hardness to cut the materials. Okay, similarly for any such applications where you need to have high hardness. Okay, and they are of course usually heat treatable. Okay, simply because you have sufficient carbon. If you have sufficient carbon, they respond well for your heat treatment, whereas for low carbon steels typically they don't respond much to the heat treatment. What I mean by they don't respond, the improvement in the hardness may not be high. What does it mean? Your hardenability, okay, your ability ease with which you can get the martensite is minimal. Okay, simply because you have very less carbon here. Okay, right. So this is the phase diagram where you see up to here. Okay, you have steels on the left hand bottom corner, always you have steels because it is the low carbon percentage, whereas once you cross, okay, this line beyond 2, it will be cast iron. Okay, now if you see low carbon steels, okay, as I said, they are less responsive to the heat treatments, and if at all you want to strengthen it, you have to go with cold work. Okay, and what it consists, typically low carbon steels, the microstructure, if you see, you already know, you have done laboratory experiments, that you see ferrite, okay, and you see the perlite. Okay, right? Similarly, ferrite is the bright phase and perlite will be like your bright and dark. Alternative phases will be existing in the form of lamellar structure. Okay, similarly, since the carbon is very low carbon steel, it will be relatively soft in nature. Okay, its hardness is not as good compared to the other carbon alloys. Okay, carbon steels. Okay, of course, but since it has low hardness, it will be having high ductility. Whichever the material having low hardness, you can take it for granted that it may have high ductility and toughness. Okay, then that is good, right? What is the goodness? What is that good? If you have good ductility, one thing is you can bring it to a different shapes by applying force, because it can easily deform, right? Similarly, it will not fail suddenly, right? And it can absorb lot of loads, okay, impact loads and so on, without fracture. Okay, sudden fracture. Okay, that means it can absorb lot of energy, okay, without failure. Similarly, it is easily machinable because it is soft. You can use in lathe or whatever machine, so that you can actually machine it. Okay, you can remove some unwanted material and bring it to a shape. And typical applications for low carbon steels are automobile body components, structural shapes, I-beams, channel, angle iron and sheets that are used in pipeline, buildings, bridges and tin cans. Okay, why bridges, buildings, they use low carbon steels even though they have low hardness? Simply because they have ductility, they have toughness, they don't fail suddenly. That is what we want when you use some material for bridges, right? Yeah. So next, in low carbon steels, if you add some alloying elements, we typically call them low carbon and high strength, or simply low alloy steels, or another beautiful name is micro alloy steels. Okay, that means you are having very low quantity of alloying elements. Okay, typically copper, vanadium, nickel, molybdenum, whatnot. Okay, you can use different alloying elements to achieve different levels of strength. Okay, so now but these alloying contents will will be less. Okay, not very high. Okay, and since you are adding these alloys, it will drastically improve the hardness. Okay, and strength, okay, of these particular steels, okay. That is what it says, okay. And also you can actually go with the heat treatment, okay. When I said plain carbon steels, plain and low carbon steels, when I actually said you cannot heat treat them because you have less carbon. Now since you have alloyed them, your heat treatability will increase, okay, because if you remember the TTT curve, the C curves will move right side, they shift to the right side by adding some of the alloying elements. If they move shift to the right side, your hardenability will improve, because even at relatively low cooling rates you can achieve martensite, okay. So next, they are of course ductile, machinable, and they have got all these good properties like resistant to corrosion and so on. And applications are, as we already mentioned, structural strength is critical, wherever structural strength is critical, so bridges, towers and so on, right. Yeah, these are some of the examples you can see against each of these steels. These are plain low carbon steels, and these are the applications, whereas low strength and low alloy steels or micro alloyed steels, you have different or similar applications you can see here, okay. Right, medium carbon steels, since you have now got little more carbon in it, now it will be much more fruitful if you actually heat treat it and quench it, you can get martensite, okay. More the carbon, also you can get higher hardness, right, and also it is higher the carbon content, its hardenability increases, okay. If you see the TTT diagrams of low carbon, medium carbon and high carbon, you can easily get it, okay. Right, so these once you heat treat them, they usually that if you quench it, you will be having lot of internal stresses, so you want to relieve them. So you usually use these medium carbon steels in the tempered condition. You already know what is tempering. If we do tempering operation to remove all these residual stresses, okay. So now the residual stresses are the excessive hardness, to remove the excessive hardness and to reduce a little bit of hardness and improve the ductility, okay. That is the tempered condition, right. So the plain medium carbon steels are low hardenabilities having, okay. To improve the hardenability, what we do, we add some alloying elements, right. If you have alloying elements, what happens, the C curves will shift to the right, and it is easy for you to convert austenite to martensite. Okay. That means your hardenability improves by adding the alloying elements, right. And if you see the applications for medium carbon steels, we use them where we need more hardness and more strength than what what you might get from the low carbon steels, okay. So similarly, high carbon steels, as we have already mentioned, these are specifically used. This of course you can harden and temper. These are you can easily harden these steels. And again, these specifically, you use these steels where you require high hardness, okay. Like for example, for tools, okay, and so on, okay. That is why the tool and die steels are high carbon alloys, okay. Where the material will be is supposed to withstand severe conditions, okay, operating conditions, like your dies where you may be having a lot of fatigue stresses, high temperature loads that are involved, okay. Well, the applications, as I mentioned, cutting tools, dies, as well as the knives, razors, okay, blades, springs and high strength wire and so on, okay, right. So if you see, try to compare, this is a stress strain diagram. First of all, what is a stress strain diagram? You can see upon tensile load for a material, how it behaves, okay. For example, initially you will be having elastic range, so where you can find the Young's modulus of the material. So after that you will find a point where the material starts deforming permanently, okay. Up to here it is only elastic range. Beyond that you have a yield point where material deforms permanently, and then you can get ultimate strength and eventually the rupture strength, okay. So using so on the right hand side you can now compare, for example, for mild steel and high carbon steel. See, high carbon steel is having high strength, whereas the mild steel is having low strength, and similarly low yield strength and so on.